I want to calculate the magnetic field due to a circular current loop. So let's first just think about a circular current loop. The magnetic field that will be induced by the current is of course in loops itself. So close to that wire, by the right hand rule, there will be a magnetic field line like that. And close to this guy here, there will be one, again, now going that way, so it'll be curling around the other way. So what happens is that the magnetic field is made of loops that come together like so, and in the centre, along the axis, they're reinforcing each other. So I want to calculate the magnetic field on that axis. Now the first thing to say is, again, if we think about those two little bits of current there and the magnetic field they generate, one guy will be creating a magnetic field in that direction, the other in that direction, they'll be equal and opposite, and so we'll be left with a resultant along the axis perpendicular from the centre of that loop. Okay, so let's draw a more detailed diagram. Here is our loop. We're going to give it radius A, and I'm going to be interested in the magnetic field on the x-axis going through the centre of the hoop and coming away perpendicularly. What I'm going to do first of all is think about just a little length of wire, delta L, which I'm going to put on the y-axis, so my y-axis will be the axis that goes through the centre of that delta L piece. Now, to calculate the magnetic field, we're going to use the Biot-Savart law. Let's first of all think about the direction. The direction is given by the cross product of the little delta L, in which the current is flowing, and a unit vector from delta L to the point that we're interested in. What that means is that the cross product says that the resultant will be perpendicular to both of these. Well, delta L is pointing out of the xy plane, so that means that our magnetic field will be in the xy plane. And furthermore, the cross product will be at 90 degrees to r hat, and that's along this line here. So here's the resultant B lying in the xy plane at 90 degrees to this line between x and delta L. Okay, let me call this angle here theta. Then this angle here will be, so that's 180, 90, so that'll be 90 minus theta. And as I just said, what we'll be interested in is the magnetic field in that direction, which when I add up opposite pieces around the loop will end up just lying in the x direction. So I'm going to be interested in the component of B projected along the x direction. So that will be, so dBx will be given by the magnitude of dB times the cosine of 90 minus theta. It's projecting here. Using a quick bit of trig, that is the same as sine of theta. And to get sine of theta, I'm now going to come to this triangle here, which has sides A and X with the 90 degrees between them. So this side is going to be given by square root A squared plus X squared by Pythagoras' theorem. So then the sine is the opposite over the hypotenuse, and this is dB's magnitude times A over the square root of A squared plus X squared. That's the contribution in the to the x component of the B field from that little delta L piece.